Alright, this is your 4.3 notes, one-to-one and inverse functions. So an inverse function, these two functions, f and g, have the property that they're inverses if we compose them together, meaning we put the g function inside the f function and we get out x. And we put the f into the g function, meaning we reverse it, and we also get out x. Okay. If that's the case, then we call g the inverse of f, or use this notation, f, and it looks like a little -1 exponent, but it's read f inverse. Okay. And then a function is one-to-one, which is part of the case when we have inverse functions. All right, they have to be one-to-one to be an inverse, or to have an inverse. But a function is one-to-one if each output of the function corresponds to exactly one input, which is kind of the opposite, or switching around, of the definition of a function. The definition of function, if you recall, is that each input corresponds to exactly one output. Now we're also adding on to that. They are a function to begin with, so that's already true. But now each output corresponds to exactly one input. Okay. So the way that we read this is, the basic way is, if this is true, if you give me two different inputs, right? Two different inputs. And we're going to call them A and B. Alright, just to call them something. But this means two different inputs. They're not equal, meaning they're different. Okay, that produces two different outputs. Alright, so if the two x's are different, then the two y's are going to be different again, not equal. Alright, so that's basically what that means for inputs and outputs. Now, determine if the functions are one-to-one. You'll have to do this in some of your homework. So to determine if they're one-to-one, we're basically going back to this definition that we're saying at the end. If the inputs are different, then the outputs are going to be different. Well, look at this. This has an even power on x. So because of that, if the two inputs are different, it doesn't necessarily mean that the outputs are going to be different. So for example, for part A, x equals 2 and x equals -2 are different inputs. Right, but if I plug them into the function f of 2, I get 3 times 2 squared, or sorry, 3 times 2 to the 4th, which is 16 times 3 is 48. And if I plug in -2, 3 times -2, or to the 4th power, -2 to the 4th power is also positive 16. And then positive 16 times 3 is also positive 48. Alright. So we had the two inputs were different, but the outputs are the same. Okay. So this is not a one-to-one function. Alright, and then for part B, we've got x cubed minus a. Or sorry, x cubed minus 1. So let's say that, let's start off saying a and b are two things that are not equal. Okay, these two inputs are not equal, so they could be like 1 and -1. All right, 17 and -3, just two things that are not equal to each other. All right, well, in this case, if a is not equal to b, then a cubed would not be equal to b cubed. Correct? If these two things were not equal to begin with, cubing them is not going to somehow make them equal after that. Okay, think about it again. A is not equal to B, so A times A is different than B times B. A times A times A, or A cubed, is not the same as B times B times B. Okay, so they weren't the same to begin with, so when we multiply them by themselves multiple times, they're not going to somehow become equal. Alright, well now if I have, again, two things that are still not equal, and I subtract the same thing from both sides, again, I'm doing the same thing to the side with the A as I am the side with the B. So if they weren't equal to begin with, and I cube both of them, they're still not equal. And then if I take those things that were not equal when I cubed them and subtract 1 from each one, they're still not equal. Alright, well what is this? This is f of A. What is this? This is f of B. Alright, and what are f of A and f of B? They are not equal. So what have we shown? Well, look really carefully. We've shown that if this is true, under the assumption that these two things are not equal, then f of A is not equal to f of B. Alright, why does that matter? It fits the definition of what we wrote on this page right here. Right? The outputs are not equal if the inputs are not equal. That's the definition of a one-to-one function. And we just showed that if the inputs are not equal, then the outputs are not equal. Okay? So f of x equals x cubed minus 1 is 1 to 1. So up here we get a yes. Alright, another way you can tell if a function is 1 to 1 or not is with the horizontal line test. Alright, different from the vertical line test in that we use a horizontal line to determine if it's 1 to 1 or not. So I'm going to put in these two functions, 3x to the 4th Alright, and this is the graph of y equals x cubed minus 1. So I've got them both in here on the slide, and just notice that if I were to make a horizontal line in between these things, okay, this one right here that we said was not 1 to 1, it fails the horizontal line test. A horizontal line hits it more than once. But if I make as many horizontal lines as I want to in this thing, even right here where it looks like it might be horizontal, a horizontal line is only going to hit it one single time at any point on the graph. Okay, so that's what we mean by the horizontal line test. Alright, now inverse functions. Two functions are inverse functions is again, if we compose them, we get x. That's what we said earlier. Notice also, if a point AB is on one function, then the point BA is on its inverse. Meaning, like if 1, 3 was on this function, 3, 1 is on its inverse. Right? Negative 2, 6, 6, negative 2, 0, 4, 4, 0. Okay? Flip the order pair around, and that point is going to be on its inverse. Alright, so this is how we check to determine if two functions are inverses of one another. We do the composition both ways and see if we get x out both ways. So this one says verify that g of x is the inverse of f of x. So I need to find f of g of x, meaning plug the g function into f and see if we get the same thing. Alright, plugging g into f means take this function right here and replace it with the x right here. Meaning this x right here is going to be replaced with all of this g of x. So we're going to take the cubed root of x plus 1. Alright, and we're going to replace that x with that. So what happens to this x? It gets cubed. So this function will get cubed, and then we subtract 1. Minus 1. Alright, what happens when you cube a cube root? It takes away the root. Alright, so these two kind of wash each other out, and we just end up with x plus 1, what was underneath the radical. And then what are we doing to that? We're subtracting 1 from it. Alright, and then the plus 1 and the minus 1 wipe each other out. And what are we left with? We're left with just plain old x. Alright, what did this thing say we needed to get? We should get x for both. Now go back the other way. G of f of x. Now we're putting the f function into g, so we're going a different route this time. Now we're taking this entire f function, all of this, and we're replacing the x and the g function with that. Okay, so what does it do? It takes the original input, which this time is going to be x cubed minus 1. It takes that original input, it adds 1 to it, and then it takes the cube root. So make sure that cube root goes above it. Alright, now we notice we just had subtraction here, so we don't need these parentheses. So once again, the minus 1 and the plus 1 are going to wipe one another out, and we just have the cube root of x cubed. And like we said before, a cube root and a cube wipe each other out, and we're left with just x. Okay, so g and f, the cube root of x plus 1 and x cubed minus 1, are indeed inverse functions. Alright, and then this is something that we want to show the 4-step process to finding an inverse function. So if you know a function and it's written in this function notation, replace that function notation with just y. Remember, they're the same thing, they're interchangeable. Interchange the x and y. Alright, switch x and y in the function, and then solve the new equation for y. Get the y isolated. Alright, so we're going to take this and do exactly what it says here. We're going to do those 4 steps to this top line here, or this top function. So the first thing said replace f of x with y. So we take f of x away, replace it with y, and we got 2x minus 1 all over 3. Okay, the next step said to switch x and y. So interchange the x and y. So we're going to have x equals 2y minus 1 over 3. Okay, so just take this x and this y and just let them switch places. That's what we did down here. And now solve for this y. Get this y isolated. So I need to multiply both sides by 3. Alright, that'll get this 3 out of the denominator. Remember, we're trying to get y by itself. So I have 3x equals 2y minus 1. Alright, and now again I'm trying to isolate this y, so I'm going to add 1 to both sides. Alright, so I got 3x plus 1 equals 2y. And then the last step to get y isolated is divide away the 2. Alright, so my inverse function looks like this. Alright, and that is what you're after, but notice the last step says replace y with the f inverse notation. If we started with function notation, we should come back to function notation. Okay, so right here at the end we'll say f inverse of x equals 3x plus 1 over 2. Alright, so there's our inverse function. Alright, and then one last property that we're wanting to show you here. If I start off with a function, so I got 2x minus 1 divided by 3, alright, and then my inverse function, which is 3x plus 1 divided by 2, alright, and I graph those. Alright, there is the graph of those two lines. Now what I want to show you, what this last property is, if I plug in the line y equals x here, the graph of these two lines are reflected over that y equals x line. So what we mean by that is, if I pick any point on the original line, say like this point on the original line, and I reflect it over the y equals x line, I'll go straight through that distance, come out, and I'll hit that. I'll hit a point on the inverse functions line. All right. Any point on the original, reflected over y equals x, the same distance, and I'll hit a point on the other graph. Okay, that's what we mean by it's reflected over that line. All right, and this last slide just shows you that I put some basic inverse functions like the doubling function 2x. Alright, and then the halving function half x. Obviously they are inverses of one another. They won't undo each other, which is what inverse functions do. And you can see again, there's the 1/2 x, there's the 2x, and then they're reflected over that y equals x line. Alright, this is the cube root function. Alright, and then the cubing function. Again, they're inverses. This is the cube root. Alright, and this is the cubing function. Alright, now what I did here was I showed you this other software. Here's the cubing function, or x cubed, and I took this line y equals x, and I used this tool that allows me to reflect this line over that line. Alright, and it gives me this. So it curves up and it goes that way. Now I also have here the graph of the cube root of x, or x to the 1/3 power, and notice that it's the exact same as what the reflected line is. Alright, so these really are the same thing, it's just reflected over that line. So that's what this last thing wants to illustrate. That x cubed, the cube root of x are reflected, their graphs really are reflected over that line y equals x. And you can see it really well with this other tool. Notice in this little region here where it makes that bend and turns, we do get this crossover. The graph, it's harder to see it with the calculator tool that I showed you here, but you can kind of zoom in on it nicely here and see that it is even reflected in those tight regions there. We still get that reflection over the line y equals x.